This is 3.6 Implicit Differentiation, Part 1. Our first objective is to find dy dx, or the second derivative of y with respect to x, when y cannot be isolated. When we're done, we need to be able to write the steps that you need to follow in order to find the derivative of y with respect to x using implicit differentiation. Before we can get there, we need to be able to connect to our old knowledge and pay attention to what we have done in the past without really noticing it. When we had y equals 3x squared, we would take the derivative with respect to x of both sides, and we would apply this operator d dx to both sides of the equation. On the right-hand side, we would apply that power rule and end up with the 6x. And on the left, we just kind of got into the habit of writing dy dx. Well, this dy dx, we now want to deliberately think about what this tells us. It says the derivative of the function y with respect to x. And what it means for us in the context of this section is that when I take the derivative of a variable other than the one I'm differentiating with respect to, I will end up with a term involving differentials. So the derivative of y with respect to x gives us dy dx. The derivative of s with respect to t will give us ds dt. Likewise, the derivative of p with respect to r gives us dp dr, and the derivative of r with respect to theta gives us dr d theta. So what this means is that we can now apply the chain rule to find dy dx with equations involving x and y when y cannot be isolated. For example, let's look at this circle that's given by the equation x squared plus y squared equals 169. If we wish to find the slope of this circle at any point on the curve, we have two options. We can do our old methodology by isolating y. So if we do that here, we can see that y will be the positive square root of 169 minus x squared, which is the top half of the circle, or we could do the negative square root of 169 minus x squared, which is the bottom of the circle. So now to take the derivatives, I would do the derivative of y with respect to x. I'd have to apply the power rule first, so there's that 1/2 times the inside unchanged raised to the negative 1/2, and then we use the chain rule and multiply by the derivative of this inside with respect to x. I can do the same thing over here, and if I simplify, I can see that I'll get a negative x on top, and that's square root of 169 minus x squared on the bottom. Well, that is the same as the y, so I can end up with dy dx equals the opposite of x over y in either scenario. With option 2, we do what is called performing implicit differentiation, and that is the focus of today's lesson. So with option 2, we have this x squared plus y squared equals 169. If I apply this operator d dx to both sides of the equation, then I can run this derivative operator through and use the chain rule as necessary when I hit different variables. So looking at this, I took the derivative of x squared gives me just a plain 2x, because the variable and the variable with which I'm differentiating are the same. If we look at the y squared term now, the derivative of y squared with respect to x will require me to hit the power first, so I'll bring the 2 down in front. I'll have a 2y to the 1 power, and then I need to multiply by the derivative of the inside. The inside in this case was a y, so the derivative of that y with respect to x gives me this dy dx. And on the right side, we have the derivative of a constant, which is just simply 0. Now that I have an expression written here, or actually an equation involving dy dx, I can isolate the dy dx. So dy dx, I will move the 2x to the other side, and then I will divide by 2y and reduce. Notice that I get the exact same answer as I got with option 1. Now, if we arrive at the same answer, then that means both of these are viable options. However, in today's problems, a lot of the time, we will not be able to isolate y. And when that happens, option 2 is our only option. So most of the problems that you'll encounter in today's lesson will force you to do option 2 as opposed to option 1. Let's look at some examples now where we have to use option 2. Looking at this, we want to find dy dx using implicit differentiation. And if you notice, in part A, I have a y squared term and a y cubed term. So nothing I do will enable me to isolate a y because this term here has no y's in it. So I'm left with having to do option 2, which is apply that differential operator to both sides of the equation. So I'm going to run that ddx all the way through, and when I hit things that involve y's, I'm going to recall that I need to use the chain rule. So if I take the derivative of y squared, the first thing that derivative is going to apply to is this squared. So I will apply the power rule, the inside unchanged raised to the first power, times the derivative of what was raised to the power. Well, the derivative of y with respect to x is dy dx. On the other side, I'll take the derivative of x with respect to x, just gives me a 1. Move through the addition, move through the constant. The next thing I hit is this power. So I'll have a 3 times the inside unchanged raised to the second power times the derivative of that inside, which was a y, with respect to x. Now notice that we did this here. We took the derivative of x with respect to x. That would just give me a dx over dx, which is the same as a 1. If I look here next, my goal is to find dy dx, and I can see that it's showing up 2 times. So in order to get it isolated, I need to get them together. In order to get them together, I'm going to collect the things that have dy dx's on one side of the equation, and the things that don't have dy dx's will stay on the other. So I'll move this whole term to the other side. I'll get a 2y dy dx minus a 9y squared dy dx. And on the right-hand side, I still have that 1. Now I have dy dx on the same side, and it's showing up in both terms. Because it's showing up in both terms, I can factor it out. And when I do that, dy dx gets written 1 time. As soon as dy dx is written 1 time, I can isolate it by dividing both sides of the equation by this factor. And I'll end up with dy dx equals a 1 divided by a 2y minus a 9y squared. And we're done. With part B, we again have an equation where y cannot be isolated, so we are forced to apply option 2, which is to do implicit differentiation. So we will apply the derivative operator ddx to both sides of the equation. And when we do that, anything that has a y in it, we will have to apply the chain rule. So on the left, I will move through the constant 2, and then I'll hit the y. The derivative of y with respect to x is a dy dx. On the other side, I'll move through. I hit a 2, so I do the power rule, raised to the 1, and then the derivative of x with respect to x is just a 1. If I do the next one, hitting the sign, the derivative of sign is a cosine of the inside unchanged, and then I have to multiply by the derivative of that inside, which is a y, with respect to x. Notice again that I have 2 terms involving a dy dx, and I have 1 term that does not involve a dy dx. So in order to isolate dy dx, I need to get them together and factor. So first I will move this one to the other side. And I'll leave the 2x on the right. Then I'll factor the dy dx so that it is written only 1 time. And then I will finish by isolating the dy dx. Last one, part C, is a little more tricky because we have a product rule involved. So with the product rule, we can see on the left we have 2 things that are being multiplied. So when I apply that operator, ddx, to both sides, On the left, I'm going to have that product rule. So I'll have the first one times the derivative of the second, and notice since the second has a y in it, I will apply that chain rule and get a dy dx at the back. So here's the first one times the derivative of my second plus the second times the derivative of my first. There's my left side. On the right, the derivative of 3x with respect to x is simply a 3, and the derivative of 5y with respect to x will mean I move through the 5 and then I hit the y and get a dy dx. Now I have two terms involving dy dx's, and I have two terms that don't involve dy dx. So I need to collect the things that have dy dx's on one side and the things that don't have dy dx's on the other. So I will move this 5 dy dx to the other side. And on the right side, I will leave the 3 and move the y squared over. Once I have the dy dx's collected, I can factor so that dy dx is written a single time. And then I can isolate it by dividing. So I'll end up with dy dx equals 3 minus y squared over a 2xy minus 5. With example 3, we want the second derivative, which involves taking the derivative of the derivative. So the notation for that, if we look here, we're taking the derivative with respect to x of dy dx. So we end up with 2 of those d's and 2 dx's. So here's the notation second derivative with respect to x applied to y. So if we look here, in order to find that second derivative, we first have to find the first derivative. So that's going to involve what we did in example 2. So I apply that derivative operator to both sides of the equation. When I do that, on the left, I will get a 6x squared minus a 6y dy dx. And on the right, the derivative of a constant is simply 0. This one only has one term involving dy dx, so I can simply isolate it. Move the 6x squared to the other side and divide by the negative 6y. If we simplify, we end up with a positive x squared over y. The goal is to find the second derivative. So now I need to take the derivative of that x squared over y. When I do that, I see that I've got the quotient rule. So the quotient rule says low d high minus high d low. Now this is where it gets a little tricky because the low is a y and we're differentiating with respect to x. So that'll be a dy dx over the low squared. Now what we want to do next is realize that this dy dx is something that we've already found. It's an x squared over a y. So the next thing I'm going to do is replace this dy dx with what it equals. When I do that, I get a 2xy minus an x squared times an x squared over a y, and that's all over y squared. Now this on a free response would be correct. However, it's kind of messy, so it's unlikely that this would show up as an answer on a multiple choice. So you need to be comfortable simplifying this and making it look better. So in order to do that, we need to get rid of the complex fraction. How we can do that is get a common denominator on the top, and then realize that dividing by y squared is the same as multiplying by 1 over y squared, which would give us a 2xy squared minus an x to the 4th. And on the bottom, I will have a y times a y squared, which is a y cubed. If we look at part B, the same process will be enacted. We're going to follow the same steps. We take the derivative with respect to x of both sides. Now notice on the left you have to be careful because you have a product rule. So when I take the derivative of the left, I will get the first one times the derivative of the second one plus the second one times the derivative of the first has to equal the derivative of 9, which is 0. If I want to isolate dy dx, it's only showing up on one side, so I can simply isolate it. I move this to the left, or excuse me, to the right, and then I divide by x squared times a 2y. When I do that, I can reduce. The 2's will cancel one of the x's, one of the y's. I'll end up with a negative y over a positive x. Now that I have my dy dx, I'm ready to find my second derivative, which will require me to do the quotient rule. Low d high minus high d low over low squared. Again, just like we did up above, we will replace this dy dx with what dy dx equals. When I do that, I will end up with an x times the opposite of the opposite. So that's going to be a y over an x. Then this is minus a negative, gives me plus a y over an x squared. Notice that the x's here cancel, and I can simply add the tops and leave the denominator. This is now my second derivative. The third variation of this part C, involves all the same steps except we add one more thing at the very end. So first we've got to find the original dy dx. We do that by applying the operator of d dx to both sides. That will yield a 2x plus a 6y dy dx equals 0. If I isolate dy dx, I will end up with a negative 2x over a 6y, which reduces to a negative x over a 3y. That's my dy dx. I'll keep that in mind when I want to find the second derivative. Second derivative is the d dx applied to the first derivative. And if I take the derivative, I again will use that quotient rule. So low d high minus high d low over low squared. Now, one of the places that people mess up is they neglect to put that whole denominator in parentheses before they square it. So they forget to square the 3, and that throws them off. Remember that this dy dx can be replaced with what dy dx equals. So now if I continue, I will get a negative 3y plus an x times a 3 times this negative x over 3y, and that's all divided by a 3y squared. So instead of dividing by a 3y squared, I'm going to multiply by a 1 over that 3y squared, which is a 9y squared. If I look here now, I can see that these 3's will cancel, and I can get a common denominator by multiplying by a y over a y. So if I combine my tops, I can see that I have a negative 3y squared minus an x squared. And on the bottom, I have a y times a 9y squared. Now the third and final, or I guess it's the fifth, however many steps we've done, is to look at that top and realize that that's the opposite of the x squared plus 3y squared. So I can actually replace this top and get negative 25 over a 9y cubed. What this means for us is that on the ellipse, the second derivative depends only on the y as opposed to the y and the x. Let's look at example 4, which requires us to find a tangent line at a particular point. Remember that a tangent line of any kind requires a point and a slope. Well, we've got the point already. It's 1 comma pi over 2. And the slope comes from dy dx evaluated at the point. So before we can find that dy dx evaluated at the point, we have to figure out what dy dx is. So this is why it's in this section. In order to find dy dx, I need to apply that operator to both sides of this equation. On the left, notice that I have a product rule. So the derivative of this one will be the first times the derivative of the second, plus the second times the derivative of the 2x. Then I move through the plus, I move through the pi, I hit the sign, it becomes a cosine, the inside remains unchanged, and then I multiply by the derivative of the inside. And on the right, I have the derivative of a constant, which is 0. My goal is to isolate dy dx. It shows up twice, and I have a term without dy dx's over on the same side. So what I'm going to do is I'll collect these two and factor so that dy dx is written only one time and can be isolated. And then I'll move the non-dy dx term, this 2y, to the other side. Now that dy dx is written once, I can isolate it and get dy dx equals a negative 2y over all of this 2x plus a pi cosine y. So remember, the goal is to find the tangent line. I've got the point. I have dy dx. I now need to evaluate that dy dx at the point. So I'll have a negative 2 times y, which in this point is a pi over 2. And then on the bottom, I have a 2 times an x, which is 1, plus a pi times the cosine of the y-coordinate, which is pi over 2. Well, cosine of pi over 2 is 0, times pi is still 0, plus 2, I'm going to have a 2 on the bottom. And on the top, these 2's will cancel, and I get a negative pi. So now I have a point, and I have a slope. I can write the equation of the line as y equals the slope times x minus the x-coordinate plus the y-coordinate, and I'm done. With example 5, this one is a little tricky. I want to find the normal lines for the ellipse at a specific point. So again, I'm finding lines, only this time it's going to be a normal line. So I'm going to need the point, which is given. I'm going to need the slope, which will be the opposite reciprocal of that dy dx evaluated at the point negative 1, 2. So we've got to go find that dy dx evaluated at the point and then take the opposite reciprocal. So again, I'm going to apply the technique that we've learned, which is apply that operator d dx to both sides of the equation. If I do it on the left, I'll get a 2x minus, and here's where people make mistakes. You got to subtract the whole derivative of this as opposed to just the first term. So I have the first one times the derivative of the second plus the second one times the derivative of the first. And that whole thing needs to be subtracted because I'm subtracting the derivative of that product. Plus the derivative of y squared is 2y dy dx. On the right, we have the derivative of a constant, which is simply 0. Now looking here, I have dy dx showing up 2 times. So to isolate it, I need to get that dy dx showing up once. To get there, I'm going to need to distribute this negative and collect the things that have dy dx on one side and the things that don't have dy dx on the other. So I'll distribute that negative first. And then I'll realize that these two have dy dx's in them, whereas these two don't. So if I collect the dy dx's on one side and factor, I'll have dy dx times a negative x plus a 2y. And on the other side, I'll have a y minus a 2x. So if I isolate dy dx, I end up with a y minus 2x over a 2y minus an x. So if I evaluate that now at the point negative 1, 2, I will have a 2 minus a 2 times a negative 1. That's plus a 2. And on the bottom, I'll have a 2 times a 2, which is a 4, minus a negative 1 is plus a 1. So that gives me a 4/5. The opposite reciprocal of that is a negative 5/4. Now that I have the point and I have the normal slope, I can write the equation for the normal line, which is y equals negative 5/4 times x minus that negative 1 plus a 2. You should now be able to do your web exam problems and write the steps that you must follow in order to find dy dx using implicit differentiation.